Hello everyone, I'm John Aguirre from the University of York here in England, and connecting today from Universidad de Sao Paulo in Brazil is Krystle, and from the Spanish Center for Biotechnology in Madrid, Marc Van Rey. Today we're doing a very special interview with two of the journal's youngest contributors, Xinping and Prashit Parikh, who have just completed a degree at FASII College in New York in the US. And with them is McLaughlin, who supervised the research as part of a program that gives undergraduate students a real experience of the X-ray crystallography workflow using pre-collected diffraction data. So welcome to Interviews with Authors. I think the first question is from Krystle.
Okay, it's very nice meeting all of you. And I'd like to start off by asking Krystle, thinking about the non-specialist public, would you be able to summarize the main findings of the research in lay terms?
Yes, sure. So one of the big public health issues is antibiotic resistance. And so a lot of research is going into figuring out new or novel targets and so that we can create new treatments. And one of the ways you can do that is by looking at the proteins in the pathogen, and figuring out the structure and maybe its function, and is it a viable target? So a lot of our work rests on that, sort of just looking to see at essential pathways, proteins that participate in them. And one of the reasons we like choosing the essential pathways is because then if you were able to, say, shut down that pathway by targeting that protein, it could kill the infection. So our research looked at a protein called FabG4, which is known to participate in fatty acid biosynthesis. That's just the term saying it makes these fats that make up the cell wall of the pathogen, of the bacteria. And so if you can disrupt the cell wall, it will die. And so the students looked at the structure of this essential protein, and we saw that we also did a test to show that it was functional. And so it's sort of the first step in characterizing this protein and the rest of this pathway.
Fantastic.
So this article is then different from others, obviously not in scientific terms, but because the lead authors were undergrads while the research was being carried out. Can you maybe explain a bit of the background of these and other undergraduate papers that you have published with us?
Yes. So this protein actually is very special in that it was the very first protein that we worked on in this kind of bigger project that has expanded. So when I got my job here at FASII, I was very committed to trying to expose as many students to research, in particular protein crystallography, which I love. I love crystallography. And I was like, this is a great method. It's not really taught at the undergraduate level a lot. I learned about it really during my graduate work. And so it was always part of my plan to figure out how to integrate it into the curriculum. But of course, it's kind of hard. There's a lot of things we already have to teach. How do we bring it in? So the first idea was to at least bring it in through the lab work, right? So maybe we don't get to teach as much theory in the biochemistry class yet, but we could expose students to the cool technique. So the department at FASII was really awesome, and they allowed me to design a new lab the second year I was here. And I chose this protein as the first one for us to study. I had heard of the SSGCID, which is the Seattle Structural Genomics Center for Infectious Diseases. It's one of the NIH-funded structural genomics centers. And so they solve a lot of structures, but they don't do any follow-up work with it. They basically collect the data, they crystallize it, collect the data, deposit it into the protein data bank, and then don't do anything else. They had put out a call on Twitter, I guess X now, looking for scientists who maybe wanted to collaborate with them. And a colleague pointed it out to me. And so I reached out to their education department, and they basically sent me a spreadsheet of all the available structures they had put in the PDB that no one had followed up on. And that's how we kind of started here. So then we had like 2 years of this pilot biochemistry lab where we studied FabG4, and the students kind of found out little pieces, and it was a really great place for me to figure out, like, I don't know, how could we do this in just a lab setting where you only have students coming in for 4 hours a week? What can we get done? What can we do? And following those 2 years, I first had Prashit come and then Xinping to follow up on some of the things that we thought students may have discovered in the lab because the data was kind of all over the place. Imagine, I don't know, 60 different students, like they were sophomores learning. And so we don't know if exactly what they did was right or not. So this is sort of the let's get a student in the lab full time. This is why they were thesis students, to try to follow up on some of those leads and finish all of the work. And so that's what they did. So yeah, so this started it. And now, since I've done that, I was able to get some funding to recreate the class, which is called protein crystallography. And we study a lot of different proteins. But this is actually the first one, even though it's not the first one we published. It just took us a little while to get it out. But yeah, I always just wanted to expose students to protein crystallography and really real research, because there's so much rich educational research out there showing that if students get exposed to a research experience earlier, their retention in science is higher, and it really makes for a better experience. So our labs, as we currently have them, the majority of labs, we know the answer. Like when you take a lab in the curriculum, you know the answer. The teacher knows the answer. You're trying to get the answer as the student. Sometimes when I teach those labs, students keep coming to check with me. Is this the answer? Is this like that we have? And so, that does have value. It does teach them techniques, but also I love like delving into a problem with them where we don't know the answer. So then if we get like say a result, then we have to go to the literature and look it up. And it's very cool to teach a class like that. So I really want to teach labs more like that, and that's where this started. And so this was the first one, and so that's why in the acknowledgement of this paper too, it thanks those two classes for their initial work, the two biochemistry labs.
Very interesting. So maybe starting with Xinping, could you tell us a little bit, maybe a bit about your background and how you got to join this project with Krystle?
Yes, of course. Prior to joining Dr. McLaughlin's lab, I had some research experience in synthetic biology, and I knew I want to do research and go to graduate school. So I think this senior thesis opportunity was really great for me to gain those hands-on laboratory experiences and also to practice my writing skill. Like Dr. McLaughlin said, she had this lab component to the class, and I actually learned about this protein FabG4 from that lab. So I think it would be good to build on my prior experience. And also I found this work really interesting because I was interested in protein and protein engineering. Yeah, so that's kind of how I got into this project.
Yeah, but I understand you did your undergraduate not at Vassar College, but in Dartmouth College, right?
So it was a engineering program where Vassar students can go to Dartmouth to study engineering. So I was a Vassar student. I just did my exchange at Dartmouth.
Yeah, that's a nice varied experience. So Prashit, could you tell us a bit about your background and why you thought the lab was interesting?
Sure. So coming into my senior thesis, I'd done some protein work in like labs over the summer, and I was looking for a project, and Dr. McLaughlin was very kind, and she offered to mentor me throughout my senior thesis. I also ended up taking her senior seminar on structural determination techniques during my senior year, so this project fit really well into that. And so I was just really interested in the topic, and also just leading an independent project during my senior year was something that was appealing to me. I knew I wanted to go on to medical school, and so having this opportunity was really valuable. And I think it was just a great experience to learn and really hone my research skills.
So did you find the sort of theoretical part interesting or difficult?
Absolutely. So when I was drafting my senior thesis, the mechanisms are quite difficult to understand, especially as an undergrad when I had just learned it for the first time in biochemistry a year prior. But I think like through that process, I gained familiarity, and then learning it again in medical school recently, it's been a very huge help. And I think just I have a very big appreciation for the project I did because it informs so much, and I'm learning more about it now as I move forward.
So Xinping, could you tell us a bit what you found the most, if there was any frustrating part of the project, and what you found the most fun thing?
Yeah, of course. So I think like any research, your experiment may fail, or like you may run into problems that your results are not very consistent. So I remember like when I was doing this project, like I think the substrate CoA was very unstable and it expires really easily. So I was having trouble to get like a consistent result, and I had to troubleshoot what went wrong, like why like my enzyme was not active. So we found out that this substrate is problematic. So we had to reorder it and we had to wait for the shipment. But other than that, I think the overall like experience was really positive. I think the most fun part was first my involvement in the lab. So as an undergrad, we have like very regular lab meetings, and I got to know other people in the lab and to hear about their project and also presenting my own work. I think Dr. McLaughlin really she really mentors the students and find opportunities for us. So I was lucky to go to undergrad research symposium to present my poster to other fellow undergrads. And it was a really fun experience. At first, I was really intimidated by the public speaking component of it, but I found people are really nice and are really interested in the work you're doing. So many people came and asked questions, and I was also viewing their presentation and talking to them. I think it was a really nice experience just sharing all those scientific findings.
Thank you very much. Prashit, do you have any anecdote you want to share with us?
Sure, I think I actually ran into the same problem when I was doing this experiment a year earlier. So it was definitely frustrating and difficult. Another thing was learning new lab technologies. I think I used, it was called NanoDrop 1C, I believe. And so building a protocol for that, figuring out how the machine works, that was difficult at first, but then I really missed it after I left because I'd gotten so used to doing it. Something I think I enjoyed is definitely presenting. Dr. McLaughlin also had me present at the PDB50 conference, which I had the opportunity to do, and that was really great. It was virtual that year, I believe, and so it was exciting to just share my project and my research in a different format, to interact with different people. And then also I just have like really great memories of going into the lab on the weekends to run experiments. It was kind of my time to just learn and have some fun despite everything else going on. So great project, and I really miss it.
Thank you very much.
Okay, this is a very interesting initiative, Krystle. But can you share with us any specific measures you take to make undergrad-led projects run well?
So one of the things that I do is try to provide scaffolding without sort of telling them the answers. So I guess being more of a support, and then really having a lot of the projects be more exploratory. So like trying to give them room, because one of the big things I want them to learn, especially as undergrads, is how do you sort of develop or go into a research question? So making sure I am there. So hopefully setting a good one introduction, right? So we have a lot of reading. Usually first I'm like, here are some papers to get you started. And then like, what is the question we want to ask? How do we answer that? Like in Prashit's case too, we hadn't even done the assay yet. He was kind of building it from scratch on what the class had done previously and using a different machine, as he said. And so I basically gave him the manual. I was like, see what you can find and we can discuss it and just come back to me. And I find that that is so much better than me giving them a protocol. I could totally write a protocol, they could run it, but there's not as much, I think, learning value in that. And so I just like to be the support and check in regularly and, sort of, they're still undergraduates. I'm cognizant that they're students and learning. So if I see maybe they're veering off course too much, I might try to redirect, but really just be a support and scaffold and help them to explore their project. So I give the origination point, right? And then let them go. And that's actually been really cool sometimes because in other projects too, students have taken the projects in places I did not expect it to go, and often have found things that I did not expect we would find. Interestingly, with this, this protein, when I first picked it, it just was notated as like FabG. Actually wasn't notated as FabG4. A student in the biochem lab found the related structure of the Mycobacterium tuberculosis one that had been solved. And then we realized a strange thing, which is that their paper said that it would use NADPH instead of, it would use NADH, sorry, instead of NADPH to do its chemistry, which for fatty acid biosynthesis is very unusual. So I was like, I don't believe this. We need to prove this, because now we know though. So I guess one of the key things I missed was that this protein, FabG4, unlike all of the other FabGs in its family, uses NADH in a biosynthetic. It's very unusual. Usually it's breakdown that's using NADH, and when you're doing a pathway where you're building things, anabolic pathway, you use NADPH. So that was really interesting. That student found that, and then we did the test, and it seemed to only work with NADH. And then Prashit was able to prove that with some really great data that had much better standard deviations than in the class with a better protocol. And then Xinping really, I think, finished the structural data for the paper too. But so again, it's that structural analysis. She did such a great job. So for undergraduates, I really just like to be a support and a guide, really.
Yeah, Prashit, looks like your weekends were very productive.
Yeah, definitely by choice. So it was fun.
Students are very motivated. I tell them they don't need to come in on weekends. I'm like, you don't have to do that, but they often get, I think, so interested in it. And because of classes, because they're undergraduates, they really don't have as much time during the week. We usually do like 4 to maximum 8 hours a week with the students that they can work in the lab during the week. And so then it's really up to them if they want to come in. So when they get fully trained and more independent, then they can choose to do that on there. But again, I do not require this at all.
That sounds great. I'm not saying I'm considering going into undergraduate training again, but if I was to take your course, what sort of training in structural biology would I receive?
Yeah, that's a great question. So this is the new course for protein crystallography. And so I've only really been teaching this a year. I've taught it twice. And so this is separate from the biochem course. In this course, we start with, as you mentioned, the pre-collected data. So it's a crystal structure from the SSG-CID that's been solved. We have that. So what do we do next? So we have this protein, and usually they have some kind of putative notation like, oh, this is a putative esterase, or it might be XYZ. So I have students do bioinformatics first. So they usually do structural bioinformatics, so trying to find any analogous structures. And I feel like that is always the most helpful because it definitely points us in the way of what is the family for sure and what might be the function. So we use DALI, we use PDB PISA. They also do sequence sequence blasting to try to find homologous proteins as well. And then I actually have them try to put together a multiple sequence alignment so that we can kind of start to find any domains, anything that, like in terms of structure, match other proteins. And from then they go into me teaching them how to analyze a structure. So what does it mean? How do we describe this? How do we talk about structures? So there's all these beta sheets and alpha helices. What does it mean? How are they arranged in space? How do structural biologists talk about these results? So we read papers. Once we find homologous proteins, it makes it a little bit easier, because then we can read papers that say might have the same domain as our protein or might have a similar active site. And we'll try to find different examples of that, and we will read through those. And then once we are done that research part, then they attempt to write their structural analysis based on this. So a lot of it starts with that bioinformatics and then putting all those pieces together to do the writing. Before we actually get to their protein, I did miss one thing. The first thing we do in the class now is a small unit on every structural biologist's favorite protein, lysozyme, because lysozyme is very easy to crystallize. There's a lot of cool data out there on it. So I start with a crash course in biochemistry, which is really just about protein structure, because the class only requires organic chemistry. So some of the students may have never thought about or even know what like an alpha helix is. So we do a crash course in biochemistry / protein structure. And then I have them set up crystal trays with lysozyme, and that's always very fun. Lysozyme crystals are gorgeous, you know, and so we talk about this, what are we doing? What they usually set up is a sort of a optimization screen, and I have them choose because lysozyme crystallizes in so many different places, they can actually just kind of pick. I give them choices, and then they can choose where they want to screen. Do they want to change pH? Do they want to change like salt? And I have them do that. Then we discuss their results. What does this mean? What would we do with it? You know, what kind of patterns do you see? I have them, you know, change the protein concentration, things like that. And so then after doing that, we talk about how you would collect data. Unfortunately, we can't collect any data here, but as I said, there's lots of cool lysozyme data sets out there to look at and analyze. So we usually just go through that as a guided one with me. And then we do this exercise in Coot that I published a couple of years ago, and students seem to really love that. You all might remember that from the lab. We did it in the biochem lab as well. But basically, I mutate lysozyme, and I give them the map, the electron density map, the mutated PDB, and I say, what we do, you know, as structural biologists is often we're going through and we're building things into the map. And I've broken lysozyme, you now have to fix it. It's kind of a fun activity also to just learn amino acids, because you have to go through and look at every single amino acid. Does it match the map? Like, does it fit well? And some places, you know, it might just be because it's disordered. So we get to talk about that. So they'll point it out to me. And I'm like, well, this is, you know, disorder. And here's what that means. And so those sort of three activities are sort of just the beginning to introduce them to how to set up crystal trays, like what's protein structure and how we might model build. And then we move on to their targets. And so the last half of the class is actually open. It just allows them to plan whatever experiment they want to either test the function of the protein, which many students have chosen to do. But in the first iteration of the class, some students chose to try to crystallize their protein with a new substrate. And then we sent it out to see if we could get new data. It didn't diffract very well, but they were really excited because they were able to grow the crystals, and then they soaked in the substrate to try to do it. You know, they only got one chance. The semester is only so long. But yeah, so the last half of the class, again, I really just try to leave room for students to explore their own ideas in like a nice guided situation, because that helps them grow, and I hope give them confidence in their ideas as well too.
And glycoside hydrolases are really cool. I just had to say it.
Yeah, no, it would be great to bring them in. Yeah, 1 year. So I'm going to teach it again next year. And I'm hoping maybe we could actually start with crystallizing the protein we're studying. Oftentimes, though, what has happened is that it's so much more complex than lysozyme that I have just chosen to go the simpler route, because it's the first week. Literally the first week of class, I'm like, hi, welcome. Now we set up crystal trays. It's like lecture, and then the next day they're setting up crystal trays. But yeah, it would be cool to just have them, you know, grow the crystal of the structure. And then we'll have those in case people want to soak in any substrates or metals or anything like that as well too. So we'll see. I'm always sort of tweaking the class so that it's a little better. From the first class to the second class, so the first time I taught it, the student feedback was that actually they needed a little bit more writing scaffolding, because I did have them write their final paper in the style of an Acta Krystle F paper. But they just said it was so hard. They'd never written a paper before. And a lot of it, what I told them was like, you know, read these papers. I gave them a lot of examples and then try to write in that style. But it was still too difficult for them. So in the last time I taught the class, I actually put in 3 in-class sessions where we just wrote together. And I walked around as they were writing, and they would ask me, like, does this sound good? Like, how do I know which part of the methods do we leave out or put in? Like, you know, so we just did that. We have these, you know, 4-hour lab periods, and we rewrote and basically had live feedback. And so I had 3 of those sessions in the class, and I think that went really, really well.
Thank you. So Prashit, you already talked about that you are now pursuing a medical degree. as graduate studies. Can you explain a bit what advantage does it have, one hand now to have a paper, and the other hand to have a good background in structural biology now?
Yeah, absolutely. So in terms of the structural biology, I think, as I mentioned earlier, I just have better insight into a lot of the protein mechanisms that we learn, a lot of the biochemistry, and also the bioinformatics aspect. I think I want to continue doing bioinformatics research. So to have that introduction was really helpful, what I did during my senior thesis. In terms of just like having a paper out there, of course, like it's helpful and like research is really interesting. And so I think the biggest thing comes from just being able to share what I've done and just have like really meaningful conversations as I move throughout my career about something that I did all the way when I was an undergrad, which seems so far now, even though it was only 4 years ago. And so, yeah, I think just like having the like basis to have like really meaningful conversations about science moving forward is like a big takeaway for me.
Thank you. And Xinping, what are your plans for the future?
Yeah, so I'm actually thinking of going to a PhD program. So right now I'm continuing my undergrad education at another institution. I was trying to expand my laboratory skills and also just still trying to find my passion here.
So you said you did some previous work in synthetic biology.
Yeah.
Do you have any ideas what direction you would like to PhD research in?
Yeah, so I've been actually in different labs. So this year I'm doing some systems immunology work. Although the topic sounds very different, but actually a lot of the workflow and skills I've gained from previous labs are very useful in my current project. Like I also do like protein purification and do some kinetic work. Thinking of the future, I think I'm really interested in protein engineering. And I think from this project, like I looked into the protein structure in very much detail, and I did some informatics work. So like I want to expand in that area as well for my future studies.
Sounds very interesting.
Yes. So, Xinping, Acta is very proud to, publish this type of article. And you have any word of advice for other undergraduate students wanting to get into research around the world?
Yeah, so I think for like if you think you're interested in doing research, I think one thing is passion that really matters to drive you forward. And I think to find your passion is really important for you to actively explore opportunities and explore like hands-on research experience in different labs. I think only by doing those things, you can realize whether you really enjoy the work or not. And I think it's very important to find people who can support you and people who you enjoy working with. And I think once you find those passion, you can easily pursue them. Yeah.
Thank you. How about you, Prashit?
Yeah, so I think my biggest thing would just be to reach out and to ask to get involved. There's so many wonderful mentors like Dr. McLaughlin who they look forward to making opportunities for students. They enjoy mentorship and like you build like a really meaningful connection. And Dr. McLaughlin has been a big part of my career and has helped me get to where I am today. And so just having the opportunity to like meet these people and learn, I think just reaching out, just putting yourself out there is like the biggest piece of advice that I would give anybody because opportunities exist and if you ask, then you shall receive, as people say. So I think it's really exciting to reach out.
Thank you.
Fantastic. Well, thank you very much for this time we've shared and all your thoughts. It's been absolutely great talking to you.
Yeah, thank you, Xinping and Prashit.
Just cut it there.
Thank you,
for joining us.
Krystle. Yeah, congratulations for the initiative. We should definitely spread the word and motivate other people to take the same.